The Oort Cloud, the most distant, vast, and mysterious region of the solar system. You've probably seen it in illustrations like these. The cloud is depicted there alongside the planets, the asteroid belt, and the Kuiper belt. And yet, we're not even sure it actually exists. We've never seen it. Sometimes when I'm researching for my videos, I come across articles on the topic I need, but in, let's say, unexpected sources. That happened when I was writing this script. I came across an article about the Oort Cloud on the website of the American organization Answers in Genesis. Basically, their creation is to believe the Earth is 6,000 to 7,000 years old, deny almost all modern science and all that. And the article about the Oort Cloud on that site, as you might guess, criticizes science. For how can this be? They talk about this region as a fact, even though no one has ever seen it. Double standards, they say. But actually, in most cases and reputable sources, there's a disclaimer that the Oort Cloud is a hypothesis, albeit one generally accepted by most scientists as the best hypothesis that explains a number of properties of our system. No one is 100% sure it exists, but you could say we're pretty sure, and there are plenty of reasons for that. That's what we'll talk about today. Why do scientists think the Oort Cloud most likely must exist? What even is it? How could it have formed? Is it possible to see it at all? And do other planetary systems have such clouds? Well, as always, you're on the Globus channel. What is it like? What do you think? If we stopped a random person on the street and asked them to draw a rough sketch of the solar system, what would we see? Probably not much good, considering that according to some polls, about 1 in 3 people think the sun moves around the Earth. And no, that's not the ones talking about frames of reference. But if we do come across someone who has at least some idea of our system structure, most likely we'll see something like this. In most people's minds, the solar system is the sun, yes, the planets with their moons. But our system also has small bodies. Yes, their total mass compared to the planets, and especially the sun, is very small, but the number of these bodies is enormous. And they're mostly concentrated in some specific areas. These are, of course, the main asteroid belt between the orbits of Mars and Jupiter, where mostly rocky bodies are found, although ice and metals are also present. We could also mention Jupiter's Trojan asteroids, the Trojans and Greeks, which are concentrated at the Lagrange points of the Sun-Jupiter system. Beyond Neptune's orbit, as we know, there's another belt, the Kuiper belt, which mainly consists of icy bodies. In all these regions, although we haven't observed and counted every single existing body, we have seen enough of them to confidently say that these are indeed special regions of the solar system with a higher concentration of bodies. In fact, all of this is concentrated relatively close together on the scale of the entire solar system. The main part of the Kuiper belt starts right after Neptune's orbit, i.e., at a distance of about 30 astronomical units, only 30 times farther than Earth is from the Sun. The main part of the Kuiper belt ends at about 50 astronomical units. Beyond the main Kuiper belt, there's also a region called the scattered disk, where the concentration of icy bodies is much lower. This region can extend up to 1,000 astronomical units from the Sun. By the way, how far from the Sun are the most distant man-made objects right now? The Voyager spacecraft. Of the 2 Voyagers, Voyager 1 has traveled farther. At a speed of 17 kilometers per second relative to the Sun, it covers almost 1.5 million kilometers in one Earth day. At the time of writing this script, it had traveled more than 168 astronomical units, or over 25 billion kilometers. As we can see, this is already beyond the main Kuiper belt, but still far from the edge of the scattered disk. This might confuse some of you if you remember the news from a few years ago. Some sources even wrote, literally, Voyager has left the solar system, considering that they have only traveled about 14 to 17% of the distance covered by the scattered disk, whose objects are quite clearly in orbit around the Sun. They are rightfully considered objects of the solar system. So the Voyagers are, and will be for a very long time, in a region where objects remain under the Sun's gravitational influence. And I've clarified many times that it's actually about them leaving the heliosphere, the region dominated by the solar wind. And where they are now, interstellar gas dominates. So, in terms of properties, this region is like interstellar space. The Oort Cloud is even further out. Since we haven't directly observed the cloud itself as a huge cluster of a vast number of bodies, we don't know exactly where it might begin. But according to current estimates by scientists, its inner boundary is somewhere in the range of 2,000 to 5,000 astronomical units from the Sun. That's from 0.03 to 0.08 light years. Estimates for the outer edge vary widely. The Oort Cloud may extend to 100,000 astronomical units. That's about 1.5 light years, and maybe even up to 200,000 Australian dollars. In short, it could stretch halfway to Proxima Centauri, the nearest star to the Sun. Even if we had a spacecraft traveling at 99% of the speed of light, it would take about 12 days to reach just the inner boundary and 1.5 to 2 years to reach the outer edge. But we don't have such technology. For Voyager 1, to get only to the beginning of the Oort Cloud, it would have to fly for another 300 years, and to the outer edge, all 30,000, if not more. Such scales and distances are quite hard to wrap your head around. Illustrations like these can help us get information, but not truly grasp how vast this region is. Here the distance scale is not linear, but logarithmic. The distance between scale steps is not the same as on a ruler. Each subsequent division on the scale is multiplied by 10. And this entire region, inside which are all the planets, the Kuiper Belt, the Sun's heliosphere, is actually 100 times smaller than this region appears on the diagram. Another main, again presumed, property of the cloud is the existence of two regions. The inner part of the cloud, at distances roughly from 2,000 to 20,000 astronomical units, has a flatter shape. And the outer part, from 20,000 Australian dollars and beyond, is a spherical cloud, which stands out in all such illustrations. It's worth mentioning that in such pictures, the size proportions of the inner and outer cloud are not preserved either. Given the sizes I just mentioned, it's clear that the inner part should be much smaller, but here it's larger for clarity. The spherical shape is one of the most interesting properties of the Oort Cloud because we're used to most things in the solar system tending toward the plane. Even Earth. Well, seriously, the orbits of the planets and most objects are roughly in the same plane. The asteroid and Kuiper belts are precisely belts, not spheres. This is due to how our solar system formed. When a shapeless fragment of a gas-dust cloud began to collapse under gravity, a protostar started to form, and the remaining matter accelerated and flattened into a protoplanetary disk, within which the planets and other bodies eventually formed. And then suddenly, out of nowhere, we have a huge sphere of icy bodies. How this came to be, we'll discuss today. The population of the Oort Cloud consists of objects whose significant mass fraction is ices of volatile substances: water, methane, ethane, ammonia, carbon monoxide, and so on. But rocky bodies could be there too. Moreover, according to relatively recent data, there might be more rocky bodies there than previously thought. In 2021, a bright meteor was observed over Canada. The body that entered Earth's atmosphere was rocky, and according to scientists' calculations, it came specifically from the Oort Cloud. This could indicate that there are more such bodies there than we thought. How many objects could be in the Oort Cloud? A whole lot. In the asteroid belt, there are over 1 million bodies larger than 1 kilometer in diameter. The distances between them, however, are also large. On average, about 3 million kilometers between two such bodies. Here, as usual, we recall illustrations where the asteroid belt is drawn as an area with a bunch of objects close together. But in illustrations, it's understandable. Our task is to show that there's a certain cluster of bodies. And in one picture, if you keep the proportions of sizes and distances correct, you simply can't properly depict such clusters of objects. But there's my favorite example of depicting the asteroid belt, which borders on idiocy. That's the movie Armageddon, of course. In the plot, smaller bodies hit Earth before the main one. And this supposedly happened because the main body flew through the asteroid belt, shown just like that. and launched a bunch of objects from the belt towards Earth. Naturally, in reality, even a body as large as in the movie would most likely not have passed close enough to any sufficiently large body for that to happen. Well, it's a movie, although there's plenty of other nonsense like that in it. But that's the asteroid belt. In the Oort Cloud, however, there could be not a million, but over 1 trillion bodies larger than 1 kilometer in diameter. True, the distance between them is also much larger, on average 50 million kilometers. And bodies larger, say, around 20 kilometers in diameter, could number in the billions, but the distance between them would be proportionally larger. Given all these presumed properties of the Oort Cloud, it might start to become clear what the problem is with detecting it. Why it's hard to see. The main reason, of course, is distance. The most distant object in the solar system directly observed by telescopes is the object 2018 AG-37. It has an elongated orbit and comes slightly closer to the Sun, but at the time of discovery, it was at a distance of about 130 astronomical units. There are known objects whose orbits extend much farther, but this one was the farthest at the moment of observation. It might be quite large in size, about 400 kilometers in diameter. Again, this is a solar system object we have observed at the greatest distance from the Sun. Now, even if we simply move such an object to at least the inner boundary of the Oort Cloud, remember the logarithmic distance scale? Not only would its angular size become 10 times smaller, but the amount of sunlight reaching it would be not 10 times, but 100 times less, because radiation intensity is inversely proportional to the square of the distance. As a result, the body would be vastly, vastly dimmer. And I'm taking a large body hundreds of kilometers across as an example. While most bodies there should be much smaller. But that's not all. The fact that Oort Cloud objects are far away hinders their observation, not only because they are visually small and dim, but also because their motion across the sky for us on Earth is very slow. Remember, we discover previously unknown objects in the solar system like this. We photograph a patch of sky at least twice at different times. Objects outside the solar system, stars, are so far away they remain in place. But objects within the solar system might shift relative to the background stars due to their orbit around the Sun. How much they shift depends on how far away they are and how much time has passed between images. The farther an object in the Oort Cloud, the smaller its apparent motion across the sky, and the harder it is to detect, even if it could be seen in principle. The story with the hypothetical Planet 9 is also illustrative here. According to the hypothesis, it should be somewhere around 400 astronomical units from the Sun, which is much closer than the Oort Cloud. That's a whole planet with a mass several times that of Earth. And even we haven't been able to see for several years now. Though there's a high probability it simply doesn't exist. But the very fact that astronomers admit that even at such a distance a whole planet of that size could be hiding, which might not be easy to see, is telling. By the way, the idea of planets within the Oort Cloud has also been discussed. There was a hypothesis that a gas giant, possibly with a mass several times that of Jupiter, could be located in the Oort Cloud. This hypothesis was put forward to explain certain orbital properties of a number of long-period comets. The story is reminiscent of the Planet 9 hypothesis, which was also proposed to explain the orbital properties of some Kuiper Belt objects. This hypothetical planet in the Oort Cloud even had its own name, Planet Tyche. It would be very far away, at a distance of about 15,000 astronomical units from the Sun. But today, after analyzing data from the WISE Observatory, it's believed that a planet with precisely those properties does not exist. However, this doesn't mean there are no planets there at all. In this article, the authors write that there is a small chance that during the solar system's formation, when it was closer to other stars in its cluster, it could have captured a planet or two from the cluster, and it might remain in the Oort Cloud. In any case, we haven't yet directly seen any planets or any other object at distances of thousands of astronomical units or more. Not one. Modern telescopes are essentially incapable of seeing them there. Probes? Well, if Voyager gets there in 300 years, it won't be working anymore. It's not even certain we'll still be around then. Even now, its cameras are turned off. But even if it were fully functional, we've already established that the distances between large objects are so vast that even if it did see something, it wouldn't be enough to conclude the existence of an entire cloud. The story is roughly similar for the newer New Horizons probe, which is currently on a trajectory to exit the solar system. And if we were to launch a new probe specifically for this purpose now, by the time it gets there, assuming our species hasn't destroyed itself in the meantime, we might have developed ways to see Oort Cloud objects without sending a probe. So maybe there's no point. The hypothesis. So why do we even get the idea that some Oort Cloud must exist? In short, the Oort Cloud is considered the source of long-period comets. More precisely, the Oort Cloud hypothesis was proposed specifically to explain where these comets come from. In short, everything here revolves around comets. Our understanding of these objects has changed along with our understanding of the solar system structure. Some comets are visible to the naked eye. In 2020, I photographed comet Neowise. You could see it with your eyes then. One of the brightest comets of the last few decades was, of course, Comet Hale-Bopp. I still remember standing at a bus stop in the very center of the city in the winter of 1996 under bright city lights, and the comet was perfectly visible. That image, I think, is forever etched in my memory. In ancient times, before modern light pollution, observing bright comets with the naked eye was even easier. Mentions and descriptions of comets can be found in historical documents thousands of years old. However, even 500 years ago, comets weren't considered cosmic objects. People back then thought they were atmospheric phenomena. But even at the beginning of the 20th century, there was no consensus on whether all observed comets were solar system objects or if some were interstellar guests. Today we know that interstellar comets do exist. We just talked about one such object, 2I/Borisov, in a previous video. But our technology has only relatively recently advanced enough to start confidently detecting interstellar objects. According to this study, about 7 interstellar objects could enter not just the solar system, but its inner part near the sun each year. Yet in all of history, we have only detected 3 such objects so far. Comets have been divided into groups based on their orbital properties for centuries. You most often hear about short-period and long-period comets. Short-period comets take less than 200 years to complete one full orbit around the sun. They are further divided into 2 main types: Jupiter family comets, with periods less than 20 years, and Halley-type comets, with periods from 20 to 200 years. Long-period comets, accordingly, have periods from 200 years up to, well, not infinity, but periods can be much, much longer. Today, we are specifically interested in long-period comets. Has our understanding of comet composition changed? Ask someone who has some idea of the difference between asteroids and comets. Most likely, they'll say, both are small solar system bodies left over from the early epochs. But asteroids are mostly chunks of rock and metal, plus a little ice. Comets, on the other hand, are mostly chunks of ice with some dust and other materials added. And it's comets that are characterized by the appearance of a coma and tails when, moving along their elongated orbits, they get close to the sun, heat up, ice sublimates from solid to gas, and ejections of gas and dust occur. Although, in reality, the boundary can be quite blurred considering that some asteroids also sometimes show signs of cometary behavior. Previously, it was thought that most of a comet nucleus's mass could be in the form of ices, sometimes up to 80%. The rest will be dust, silicates, and so on. You may have heard comets compared to dirty snowballs. In fact, one hypothesis of comet structure is called the dirty snowball hypothesis. Wow, another gigantic episode, it seems. Hope you found it interesting, friends. Every time I sit down to write a new script, I need to try not to go overboard this time to not have to sit writing scripts until night every day. And in the end, I dig up so much information that I end up sitting late into the night writing the script to meet the filming deadline. But I hope it wasn't in vain. I hope you enjoyed it. See you soon.